Welcome to the video. We'll cover characteristics of waves, electromagnetic spectrum, and refraction. Let's go through the things that you need to remember, the main concepts of this unit and this video. So what are the general characteristics of waves? Gives 3 to 5 examples of waves in the real world. Explain the difference between transverse and longitudinal waves and give examples of each. Describe the basic properties of waves. Include the frequency, amplitude, wavelength, and the positions, such as the crest and trough. And what are the units, let's say, for frequency? So describe the electromagnetic spectrum. Talk about the characteristics. So think about, for example, radio waves versus visible light versus gamma rays. Describe the frequency, amplitude, wavelength, energy for radio waves versus, let's say, visible light or gamma rays. So list the waves in order, from AM radio, then FM, all the way to gamma rays. Explain the difference between light and sound waves. If the frequency increases in a wave, what happens to the wavelength and the energy of the wave? Light can be explained as having 2 forms. How? This is going to be a little bit challenging, so make sure you pay attention. And describe refraction and explain 2 examples when you see refraction. Again, as always, write down questions, comments, notes, and then let me address any questions that you have in class. So just think about waves in your life. Just thinking about going down to Lake Superior, down to Buc-ee's, and all the waves have a similar shape. So waves carry energy and sometimes information over long distances. So sound waves, certain waves like sound and earthquake waves, P waves, need a medium, need a substance to go through, such as longitudinal. Again, sound is an example of longitudinal wave. So think about water waves, sonar waves, so dolphins, whales. Think about radio waves. There's other ones that do not need a medium, a substance to go through, like light, AM radio. And again, these are transverse waves. These are the electromagnetic spectrum. So then 2 main types of waves that you have to differentiate or tell the difference between. So transverse, again, so the oscillations of particles move perpendicular. So think about a little yellow rubber ducky on the waves moving up and down, up and down, up and down, as the wave actually moves towards the shore. So the wave is moving in one direction, but the particle, or rubber ducky, just moves up and down. So it's perpendicular. So think about this T for transverse. Do this with your hand like a timeout, and then flip it. So T upside down, it's perpendicular sign. Another thing about that stadium wave we did in class. So you as a particle, as a observer, moves up and down, but the wave moves along the stadium. Longitudinal is a little bit more difficult to visualize, but the particles move in the same direction of the wave. So imagine a slinky. This is my best example here, is that you can squish or compress part of it, and then when you let it go, that compression moves the whole length of the slinky. So these particles move in the same direction as the wave. Again, think about sound waves. If you could actually see sound waves, they actually compress the air, and then it moves into your ear, to your eardrum, and your eardrum actually vibrates. So again, longitudinal, these need a substance to go through. These need a medium. So frequency, just how frequent are the waves? So if this was 1 second, you'd have a lot of waves, high frequency, versus this low frequency, only 2 waves in 1 second. So amplitude, again, think about plugging a guitar into an amp. What does the amp do? Increases the amplitude, or the height of the wave. So for a guitar, it would be louder, so it adds more energy. The greater the amplitude, the greater the amount of energy. And so the top is called the crest, the bottom a trough, just kind of like what horses drink out of, a trough. And wavelength, you can measure from peak to peak, you can measure from trough to trough. I like to start at the line, then go up, down, and back. So You have just half of the wave on each side. So on a quiz or test, if I have two different waves drawn together, be able to tell the difference between them. So which one has a greater amplitude, frequency, wavelength. So both of these have the same wavelength, so they both have the same frequency. So what is different? So the electromagnetic spectrum, these are the transverse waves. So they're always perpendicular. So the particles move up and down compared to where the direction of the wave. Now these can go through a medium, a substance, but they don't always have to. And we need to make sure we remember these in order. So what this diagram is trying to show you is that the radio waves are as tall as skyscrapers or mountains. And then as we go through, these waves are getting smaller, smaller, smaller. Ultraviolet, the waves are the size of a virus, very, very small. X-rays the size of an atom. And gamma rays the size of the nucleus of an atom. So very, very small waves. High energy. So, looking at these types of transverse waves, electromagnetic spectrum, we do have to compare their frequency and how much energy. So radio has the least amount of energy. So it has a long wavelength, a low frequency. But the gamma rays, as we move from left to right, these have a high frequency, short wavelength, short distance between the crest and crest, and these have a very high energy. These will kill you. I threw this in here too, just so you can see that television waves fall in here, XM radio, and other ones. At some point, if you're going to college, you might actually have to memorize the light spectrum. So 760 nanometers to 300, maybe 380, sometimes 390 nanometers. Remember, violet has more energy than red. So we go infrared, which has less energy. Then we go to red, which has a little bit more, to violet. What has more energy than violet? Ultraviolet. So, thinking about it, the speed of sound versus speed of light. So light travels very, very fast. So 300,000 kilometers per second, or 186,000 miles per second. That's pretty fast. So from the sun to the earth, it's right around 8.2 minutes. So if the sun ever extinguished, we wouldn't know it for, well, a couple minutes. Sound, much slower. 348 meters per second, or right around 750 miles per hour. Now this can change depending on the density of the air, the temperature of the air, etc. Now if you're at a track meet, this kind of seems to make sense. If you're running like the 220 and someone's going to start shoot the starting gun, you see the smoke before you actually hear the gun. So just think about that. So the speed of sound is slower than the speed of, you can see the speed of light, you can see the smoke before you can hear the sound, because sound is slower. So this is a picture of a jet breaking the sound barrier, which happens right around 750, 742. And the interesting thing is, if it keeps exceeding this speed, it keeps breaking the sound barrier, and so you actually have a shock wave. If it's lower to the ground, it'll shatter out windows and possibly hurt your eardrum. That's why most jets have to fly above 10,000 feet. They call it the hard cap. So once you think about it, if I have this wave here and I increase the frequency from here to here, I have more waves per second. So what I'm doing is really squishing these waves together so that now I have a shorter wavelength from crest to crest. This is a shorter space. The waves are closer together. This gives it higher amounts of energy. So as I increase the frequency, I'm decreasing the wavelength, and that ultimately increases the amount of energy the wave has. And then also you can increase the energy by increasing the height of the wave, like so. Now this is kind of an interesting, kind of a mind-boggling idea, but light, but really anything in the electromagnetic spectrum. So anything from radio waves, microwaves, infrared, visible light, all the colors, red, purple, blue in between, X-rays, ultraviolet, and gamma rays. All of them can either be classified as a wave or these photons, like a little bundle of energy. So as far as light goes, a little bundle of light particles. So in some experiments, light or radio waves behave like a wave, but in other experiments, it actually demonstrates more of a photon or a particle characteristic. So it could be either one. So this is where the little comic strip, am I an X-ray photon or a wave? Heck, why worry about that again? I'm not even sure if I'm a wave or a particle. So a little science humor. So we've all put a pencil or a straw in a glass of water and then it looks like it's broken or bent. And so why does that occur? So the scientific term is called refraction. So it has to do with light. So we know that light leaves the sun and is traveling something like 300,000 kilometers per second or 186,000 miles per hour, miles per second. And so it goes really fast through outer space because there's nothing to slow it down. Then it hits our atmosphere, and then what happens? It slows down a little bit. So as it's going through air, it's going a little bit faster. And then when it hits water, water is more dense. So then the light slows down a little bit more. So it's this changing of speeds as it goes through a new medium or substance like water because it's more dense. So we're really seeing the light reach our eyes that's going through air, and we're seeing the light going through the water, and so we actually see two different perspectives at two different speeds, and so that's why our mind, our eyes, interpret that as being bent or broken. Now that you've gone through the video, also go back through and then make sure that you've written down all the information on your reading guide and that you're focused on that information. So, examples of real-world waves, difference between transverse and longitudinal waves, big difference. Longitudinal is a little bit more challenging with the sound and P waves from earthquake waves. They move in the same direction. So, be able to explain frequency versus amplitude versus wavelength and position the crescent trough in the units, like hertz for frequency. So, on electromagnetic spectrum, make sure you know which one has the highest frequency, wavelength, and energy. Be able to list in order from radio waves to gamma rays. What is a mnemonic or memory pathway in which you can try to visualize and remember this order? So be able to explain sound waves versus light waves, wavelength and energy, the frequency. Can you explain this information to somebody else? So how can light or other transverse waves have different forms, and be able to describe refraction in your own words. As always, make sure you write down the questions and let me know how I can try to explain it to you in a different way or give you different examples. Thank you.